Hey, Rose, let me have a look at what that question says, and I will let you know my advice. Okay, so let me sketch out what this is asking for. So 28 is saying prove that if S union T, sorry, prove that if S and T are shifty, so is S union T. So, what does it mean for something to be shifty? So remember the definition here is that a set A is shifty if for all x in A we have x minus 1 is in A or x plus 1 is in A. Okay, so let's suppose that S and T are shifty. Okay. So we want to show S union T is shifty. Okay, which is to say, if I write it out, that is, I want to show that if X is in S union T, then X minus 1 is in S union T, or X plus 1 is in S union T. Okay, so far, I've written the definition of shifty a bunch of times, basically. But this is what I have to prove. Do we agree this is what I have to prove? So, in order to show this, I need to start by supposing X is in S union T. So, where are my cases going to come from? Right. So X being in S or T means that X is in S or X is in T. And you can't really make any progress until you know which of these it is. So, thus, X is, or sorry, so then you want to structure this as case 1, X is in S, case 2, X is in T. And now, as Thandika suggests, once you know that X is in S, well, now you still have to decide whether X minus 1 is also in S or X plus 1 is also in S. And so then you might have subcases for each of these cases. But that should give you enough to understand how to structure this proof. Are there any questions about that? how did I know to suppose X was in S union T? I knew to suppose X was in S union T because when I wrote out the definition of shifty, it was this. And so, oh, there's a N missing here. So this is just verbatim the definition, spelled out, or almost verbatim the definition. And so this is an if-then statement. So the way I prove an if-then statement is to suppose the if part and get to the then part. Yeah, so I guess when I copied the definition, I went from for all x in A to if x is in A, but those two are equivalent formulations. So for all statements can be rewritten as if-then statements, and I just wrote it as an if-then statement to make it easy to prove or structure. That's the implication. Which implication when you say the implication? So you're already at this point in the proof of that implication. So you've already supposed this part. So broadly, the thing you're proving is an if-then statement. But then once you're in the process of proving the then part and you write out what it is, that is also an if-then statement. And so then you have an extra piece of suppose. And so when you actually want to type this up, probably the first sentence would be, suppose S and T are shifty and X is in S union T. But you're not going to know that until you figure out sort of how all the pieces fit together. But basically, when you have an if-then statement where the then also has an if-then statement in it, then you get to basically pull all the ifs out to the front. That's basically what ends up happening. Okay, there was a question also about 35, but I'll give this just a second in case anyone has anything else they want to say about shifty sets before we talk about 35. Okay, so 35 is about this whole non-differential business. So a set S, which is a subset of the integers. Yeah, so for every x and y in S, we have x minus y is not in S. Okay. So then 3b is prove or disprove if S and T are non-differentiable, then so is S intersect T. And so first question, I suppose, is based on what you've done and thought about, do you think it's true or false? And I agree, this is true. And in fact, there's going to be echoes of the example we just did here when we prove this. So my proof here is going to have to start with supposing these things are non-differentiable. Sorry, non-differential. Now I want to show that S intersect T is non-differential. So I'm going to do this on a sheet of scratch paper just so that I can keep this proof clean like it would actually get written up. So what do I want to show? I want to show S intersect T is non-differential. Okay, which is the same thing as saying that what I want to show is that if x and y are in S intersect T, then x minus y is not in S intersect T. Okay, do we agree with my restating what it is we're trying to prove? So ultimately that means I'm going to need to suppose this piece. So I'm going to suppose S and T are non-differential and x and y are in S intersect T. Okay. And what I want to show you is that x minus y is not in S intersect T. So thus, because x and y are in S intersect T, x and y are also in S. And so since S is non-differential, x minus y is not in S. Thus, x minus y, I should go ahead and just put this on the next line, x minus y is not in S intersect T. But if you look at what I've just done, I've just proven that S intersect T is non-differential because I've shown that if I take two arbitrary elements of S and I subtract them, I've shown if I take two arbitrary elements of S intersect T and I subtract them, then the result is not in S intersect T. Okay, so this is not so different from the shifty example we talked about a minute ago. Now, when you actually sat down to write this for the first time and you did your scratch work, probably you would have written down, okay, so what do I know now? So I know x and y are in S and x and y are in T. And you might have at first said, okay, so x minus y is not in S, and x minus y is not in T. But then when you want to write this down, you might have then said, okay, so x minus y is not in the intersection of S and T, which is certainly true, but in fact x minus y is in neither S nor T, but you don't actually need to know both of those in order to prove the statement that you're asked to prove. So probably when you write scratch work, you write a whole lot more until you then go and carefully write up your proof and get something like this, where you realize, if you look at this closely, that you were actually given more information than you needed. You did not need to know that t was non-differential in order for this result to be true. Does that give you a sense of how to approach this kind of question? Very often the key is going to be in your scratch paper, sort of writing and rewriting until the thing you want to show is now just an if-then statement, because then you know how to formulate an if-then proof. Can x and y both be the same number? X and y can absolutely both be the same number. Yeah, so that if you have different variables, mathematicians will never assume that those variables are not equal unless that is expressly stated. So it's very possible that x and y are equal, which may have relevance for question 35D. Can I talk about 31? Yes. So here's my hint for 31. And this is really my fault. Do number 33 first. This was my bad, so I reorganized the order I did the sections to try and put the homework in an order that was doable on this schedule, but then that meant that I moved something. I moved question 31, which 33 is very useful for, to afterwards, which was bad. But what does 33 say? 33 says that part of what 33 says is that if n is a multiple of 3, then there exist consecutive integers x, y, z such that n is x plus y plus z. But note, consecutive integers are definitely distinct. So effectively, this is one case of 31. And so then you have to figure out how to modify this one case of 31 to handle numbers that aren't multiples of 3. And so you might correctly guess that there's going to be 3 cases: the numbers that are multiples of 3, then the numbers that are 1 more than a multiple of 3, and then the numbers that are 2 more than a multiple of 3. At least that's how I would go about it. Does that give you enough to get started, Kratib? Sure, May. 34. So 34 prove that if A and B are both subsets of R, and A union B complement is R if and only if A is a subset of B? No, B is a subset of A. Okay, and here for purposes of that complement, we're making the agreement that our universal set here is the reals, which means B complement is just the same thing as R minus B if you're playing the home game. So we've got two directions here. And so the direction you said you were struggling with was the backwards direction. Okay, so the backwards direction says if B is a subset of A, then A union B complement is R. And so here's my hint. Prove the contrapositive of this. Which is if A union B complement is not the reals, then B is not a subset of A. And just to give you a sense of how does that get started, so I'm going to suppose A union B complement is not R. Okay. So since A and B complement are subsets of R, this is really saying that A union B complement is a proper subset of R. Okay, where this is my proper subset symbol. And so being a proper subset tells me something. Namely, it tells me there's an element in R that is not in A union B complement. And so what does this say? This says X is not in A and X is not in B complement. But X being an R that's not in B complement is exactly saying that X is in B. And I'll leave you to sort of think about from there, but you're sort of almost there once you've thought about it that way. Okay. Kratib asks about the contrapositive of the statement if n is a multiple of 3, then there exist consecutive integers x, y, z such that x plus y plus z is n. So the contrapositive here is if for all consecutive integers x, y, z, we have x plus y plus z is not n, then n is not a multiple of 3. For what it's worth, I do not think this is a helpful contrapositive, but that's what the contrapositive says. Other questions we want to talk about? I believe G is false. How would you disprove it? So this is really a statement about all non-differential sets, right? This is, again, sort of going back to our translating back and forth between an if-then statement and a for every statement. This is saying the same thing as for every non-differential set S, the set Z minus S is non-differential. And so to contradict a for every statement, we tend to use a counterexample. So here a single counterexample will do. And it's actually super nice in this case because you cannot find a thing that is not a counterexample to this. Because in fact, actually, it's even true, actually, that for every non-differential set S, the set Z minus S is not non-differential. So take your favorite non-differential set, like 1, 3. Then z minus s is z minus 1, 3. And so, for example, say 7 and 2 are both in z minus 1, 3, but so is 7 minus 2 equals 5. So z minus 1, 3 is not non-differential. Something like that. Now, if you put your question about this thing with complements together with Kratib's question about non-differential sets never containing the element 0, then you might realize that you could actually short circuit all of this by saying, okay, S is a non-differential set, and so S doesn't contain 0, so Z minus S does contain 0, but we already proved that no non-differential set contains 0. So that is my recommended approach for that. Does that make sense, May? Upon rewriting, I would probably give Z minus S a name so I could stop writing Z minus S over and over again. I would probably say then T colon equals Z minus S, and note that 2 and 7 are in T, but 7 minus 2 equals 5 is also in T, and that means it's not undifferential. But that's just sort of like cleaning up what I wrote here to look a little nicer. Okay, so why can't a non-differential set have 0 in it? That is the question. Does anyone want to offer an explanation as to why a non-differential set can't contain 0? Right, because x minus x equals 0. That is a beautiful proof. And I think I can even simplify that proof to actually say 0 minus 0 equals 0. And so, in fact, what you're really doing here is you're really proving the contrapositive, which is you're proving that if 0 is in a set, then it's not non-differential, because then you can write down a difference of things that is in the set. Yes, they should be rows. They should, all of these you should be able to write up formally. Although, of course, for lots of them it's a disproof, so that means basically the quote unquote formal proof is this is a counterexample. Let me know if more questions arise. I will be here. Okay, let's look at this. So, 33. So 33 says that, sorry, if n is an integer, then n is a multiple of 3 if and only if... Did I write this backwards of the way that it is in the packet? So yeah, sorry. And n is a... I'm just going to write it the same direction so that our arrows point the same direction. Then n is a sum of 3 consecutive integers. If and only if n is a multiple of 3. Okay, so you said you had the forward direction, which was if n is a sum of 3 consecutive integers, then n is a multiple of 3. That was the one you were happy with? Okay, so when we go to write this proof, it's going to start with, suppose n is a multiple of 3. But then we're going to maybe realize that I need to actually give examples of x, y, and z, and I don't know what those examples are off the top of my head. Now, if you feel like being clever, you can spend not a whole lot of time and you might be able to think about the answer, but you can also just go over to Scratchwork land and think about what's going on. So n is a multiple of 3, so that means n is 3k. And I want x plus y plus z to be 3k. If x, y, and z are consecutive, well, then y is x plus 1 and z is x plus 2, right? And so then what we're saying here is that x plus 1 plus x plus 2 is 3k. So that is 3x plus 3 is 3k. So x is k minus 1. And actually, if you look at this, you can actually sort of see what's happening here. If x is k minus 1, then y is k and z is k plus 1. And so really sort of this is the heart of it. This is the thing that you either solve for the way we just did or sort of guess that if I want 3 consecutive integers that sum to 3 times k, I add together k minus 1k and k plus 1. Okay, and so basically this proof is this long. Because this is a proof where I'm proving a for every there exists statement. And so I need to give you an example for every possible n. So that is every multiple of 3. I need to show you how to write it as a sum of 3 consecutive integers. But I've done that here. So I've given you this formula to do it. Does that make sense? Other questions we want to talk about? All right, folks, if there's no more questions, I'm going to duck off here. Have a wonderful afternoon, and I'll see you tomorrow. Feel free to email me if any last-minute questions pop up as you're working through this. And I will see you tomorrow.